So at the end of the day, we're working on the electric chain hoist question here, and we notice there's a couple of problems with the information we're given. Okay, as we try to draw the free body diagram for this, we realize we don't know what the mass of the engine the hoist is lifting. Okay, we don't know what it is. And that's going to make things difficult because as I start putting forces on here, okay, I have the force of the hoist, which is, according to the question, 2,850 newtons. And then obviously, because it's lifting something, it's working against gravity. But I can't calculate gravity because I don't know the mass of the engine. So I'm kind of at an impasse here in that I don't have enough information to get the forces I need to use the sum of all forces in order to get the net force. All right. Now, the other thing the question gives me is the net acceleration. This is the acceleration of the engine being lifted by the hoist. All right. So what we have to realize is that F net is the vector sum of all forces. So that would be the force of the hoist plus the force of gravity. The same is true for the accelerations. Okay. The net acceleration is the vector sum of all the accelerations, just like it is for any vector quantity. Okay, if I'm looking for the vector sum of anything, I add all the other vectors together. So what I can essentially do is say that F net is mass times acceleration. I can say that the hoist is mass times the acceleration the hoist would produce if it was all alone. Okay, didn't have gravity to work against. How fast could it accelerate something? Okay, plus mass times the acceleration due to gravity. We calculate any force by multiplying mass by whatever the acceleration that force could produce is. Okay? Now, the question wants to know what the mass of the engine is, but before I get to that, I actually have to cancel the masses. Because if I can use this formula here, the force of the hoist equals mass times the acceleration of the hoist, I can use that to get mass, as long as I can get this number, the acceleration of the hoist. Well, mass is in every term here. Agreed? Okay, so I'm going to cancel it off. It's like it doesn't exist. So the net acceleration is the acceleration of the hoist plus the acceleration due to gravity. I know what the net acceleration is. It's 1.5. And I know what g is. It's negative 9.81. Can I find the one force that I don't have? Or sorry, the one acceleration I don't have? Okay, so I'll have the acceleration of the hoist is the net acceleration minus the acceleration due to gravity. All right, so when I do this, the acceleration of the hoist is going to be 1.5, positive 1.5, minus negative 9.81. Okay, everybody follow what I'm doing here? When I do that, I'm going to find that the acceleration that could be produced by the hoist, if it was all alone, is 11.31 meters per second squared in a positive direction. Okay? Which makes sense. If it's going to lift something against gravity, it needs to produce an acceleration up greater than gravity. Right? It would be exerting a force greater than gravity to move up as well. Okay, now that I have the acceleration of the hoist, I can go back to this. The force of the hoist, which I know, is equal to mass times the acceleration of the hoist. Now I can find mass. Okay, I couldn't find it before because I didn't have this number. So the force of the hoist divided by the acceleration of the hoist equals mass. So that'll be 2,850 divided by 11.31, okay, and that should give us 252 kilograms. Okay, that is what we call the differential acceleration method. It is very rare that you will encounter a question that requires you to do it. And when you do, it will be an elevator question. Okay, so it's not often that you encounter a question that requires you to do this. But it's still important to recognize that the relationship between force and acceleration is the same, okay, in terms of their nets are the vector sum of their components. Okay, everybody all right with that? This question requires you to use the net acceleration method. Okay, a skydiver is an elevator. All right, anything moving vertically is an elevator question. Gravity is there and air resistance is there. All right, I'm going to give you a few minutes to give this one a try. So they've drawn for us both the free body diagram as well as a vector diagram for us. Okay, the vector diagram is here on the left. Okay, showing that we have the force of gravity. Okay, going downwards. We have the force of friction or air resistance going upwards, and then our net force is the purple arrow here. Okay, the same would be true for a net acceleration diagram. Right, there would be the acceleration due to gravity, 9.81. There would be the acceleration due to friction, which we don't know, and then there's the net acceleration, which we're told is 5.96 meters per second squared. So we'll just do a sum of all accelerations calculation to get the acceleration that would be produced by air resistance alone. Right? So we'll have that the net acceleration, so A net equals G plus the acceleration due to friction. Okay, so AF. So we're going to bring G over by subtracting it. So we'll have our 5.96, which is negative, minus negative 9.81. That's gravity, and that will equal the acceleration due to air resistance. So when we do that, we'll have negative 5.96. Whoop, not 59.6. 5.96 minus negative 9.81. Okay, so 3.85 meters per second up is what the air resistance is causing as an acceleration. All right, so sorry, 3.85 meters per second squared. All right, now that we know that, we can use this, which is the force of air resistance, to calculate the mass of the skydiver. Okay, so the force of air resistance is equal to the mass of the skydiver times the acceleration due to air resistance. Okay, so we're going to bring over the acceleration due to air resistance, and that will give us mass. So we got 250 divided by 3.85, and that will tell us the skydiver's mass. So, all right, so the skydiver is 65 kilograms. Okay, so like I say, differential acceleration problems are very rare. Okay, but it's just important for us to realize that we can do net acceleration calculations in the same way we can do net force calculations. All right, try number 1, and we'll talk about number 2. You can write down some answers for number 2. There's not really any calculations for number 2. Okay, there is a calculation for number 1. So we'll have you try number 1. It's not differential acceleration. Okay, and then we'll talk about it as well as number 2. Okay, so I'll give you a couple minutes on those ones. Okay, so a bungee jumper is still an elevator. Okay, we have an object that is moving vertically. There are forces acting on it. One of those forces is gravity. The other force is the bungee cord. Right. So what we have for a free body diagram is our 55 kilogram jumper being pulled downwards by the force of gravity, okay, which we can calculate because this time we know the mass. So we'll have 55 times 9.81, right, which will give us 539.55 newtons. Okay, and they tell us that the force upwards from the bungee cord is 825 newtons. So obviously my lines are not to scale here, but okay, we got 825 newtons up. We've got 539.55 down. Can we calculate her net force and thus her acceleration? Okay, so net force is the vector sum of all forces. So that'll be our 825 minus our 539.55. Okay, in other words, the force of the bungee minus gravity. Okay, or plus the force of gravity, making it negative. Right. So when we do that, okay, so we got 825 minus our answer there. So our net force is 285.45 newtons upwards. Okay, and then from there, we want to calculate her acceleration. Well, acceleration is F net divided by m, so 285.45 divided by her mass, 55. Okay, and we get 5.2 meters per second squared up. Okay, and you definitely want your acceleration to be up when you are bungee jumping. Okay, I mean the first part's down, but up after. So it must not have been that completely different. You probably ended up doing the differential acceleration method. You can actually do that with this. It's more work on this one. Yeah, exactly. So you went and did the differential acceleration method, which actually has extra steps compared to what I did. But it gets the right answer. There's nothing wrong with that. Okay. All right. So when you bungee jump, this is for question number 2. Obviously, the first part is the free fall part. That's the exciting part. Okay. You're falling towards the riverbed, canyon bottom, whatever it is that you jump off that bridge. Okay. So as you're falling, you're accelerating due to gravity. The instant that the bungee cord starts to take up, your acceleration switches. Okay, like not immediately to up because that would cut you in half. Okay, but it doesn't do that. But it does very quickly change from being downwards to now being upwards. If it didn't, you wouldn't what? Yeah, you wouldn't stop. You wouldn't slow down. Okay, so as soon as that bungee cord begins to stretch, your rate of acceleration changes and very quickly becomes a positive acceleration. You're still moving down, but you're accelerating up, which means you go slower and slower and slower. So you get that moment of, wow, my face got really close to the river, and then you get shot back up into the air, okay? Which is like also apparently exciting. I don't know, I've never done it, okay? So that's all they're asking there. Compare the direction of the acceleration at the lowest point in the jump. At the lowest point in the jump is where your acceleration is at its maximum upwards, because that is where you have stretched the bungee cord its maximum amount and where it is pulling the hardest. The more you stretch the cord linearly, the harder it pulls. Okay, everybody follow me there? All right, and so that's what you want it to do, right? So at this point, what's the direction of your acceleration? It's obviously up. Okay. All right, questions on any of those? Okay. This is where we need to talk about objects versus systems, okay? If you have an elevator question that doesn't have anybody in it, like so it's just an elevator going up and down, there's no occupants, that's just an object. We're only talking about the elevator, all right? In this question here, I have a 20 kilogram block and a 10 kilogram block. I have 2 objects and they're connected. Hence they are a system, right? Because whatever happens to those blocks, they have to accelerate at the same rate because they're connected. All right, they have to accelerate at the same rate because they're connected. They're essentially just one object. Okay, I mean, there's 2 separate objects here. We can treat them separately, but they are part of a system that will move and accelerate at the same rate. That's what we have to remember about systems. All parts of the system have the same acceleration. The forces acting on the separate objects are different, okay, but they contribute to this unified system acceleration. Okay, so I've got 2 blocks and they're made of identical materials. They're connected by a light rope on a level surface. There's an applied force of 55 newtons to the right. Okay, so the hand there, okay, is pulling with 55 newtons to the right, and the blocks are accelerating. While in motion, the magnitude of the force of friction on the block system is 44.1 newtons. Okay, calculate the acceleration of the blocks. All right, can I simplify this diagram a little bit? Right? It's asking about the blocks combined. It's saying the force being applied on the blocks is 55 newtons. The combined force of friction on the blocks, plural, is 44.1. So really, I can just draw this like this. Agreed? Okay. These questions only get complex when they start saying, there's a force of friction on this block of this much, but the other block's being pulled by this much force. Okay, and then you have to start separating them, okay, and dealing with forces individually on objects. But always remember, even if you have to do that, the acceleration of both blocks is the same. Okay, that's the one thing you know. All right, so if I'm looking at this then, my overall net force here is going to be 10.9 newtons, right? 55. So my net force on the whole system is going to be 55 newtons minus 44.1 newtons, okay, which should give me 10.9 newtons forward. Okay, now I want to calculate the acceleration, so I'm going to take that net force and divide it by how much mass? 30. Remember, the whole system is accelerating together. Right? So I combine the masses here. Okay, 10.9 newtons divided by 30 kilograms, okay, will give me my total acceleration for both blocks. Okay, so we got 0.36 meters per second squared forward. Okay, so that's a simple system question. Now the question could get crazier and give you a part B saying, all right, there's this much friction on the 20 kilogram block. How much tension is there in the rope between them? Not as hard as you might think. Okay, do I know the acceleration of the 20 kilogram block? I just calculated it, right? Because I calculated the acceleration of the system. So if I know the mass of the block and its acceleration, I can calculate its, what's mass times acceleration? Its net force, right? So I can individualize the system and just work with parts of it, okay? And I can combine the system. What I need to remember, regardless of whether I'm combining or isolating, is that the acceleration of both parts is the same. Okay, I already calculated it, so I know what it is for the 10 kilogram block. I know what it is for the 20 kilogram block. All right. Okay, so on that note then, I want you to try question number 2 first, okay, because it has to do with the one we just did, right? So remember, we already calculated that the acceleration is 0.36 meters per second squared forward. Okay, now it says the force of friction on the 10 kilogram block is 14.7 newtons. Calculate the tension in the rope connecting the two blocks. Okay, and then calculate, this is, B is dumb, I don't know why they ask you to do this. What's the tension in the rope between the hand and the 10 kilogram block? No, what's the tension in this rope right here? 55. I don't know why they ask you to calculate that. They told it to you in the question. It's like the dumbest question ever. Okay? Be easy marks though if someone ever gave it to you. All right, so you don't have to do B because B's dumb. They gave it to you. Okay? But try A. You can solve for that using either block. It doesn't matter which block you use, you can arrive at the correct answer. So you can use the 10 kilogram block or the 20 kilogram block. Draw a free body diagram of the individual block you choose. Okay? That's the hint I'll give you to start with. So there's 2 ways to solve this. Okay? I'm going to separate the screen into the 2 ways. Right? So this is going to be the block 1 method. Okay? So using the 10 kilogram block. And this will be using the 20 kilogram block. Okay? The 20 kilogram block might be the easier one to use. Okay? So here's what we have to consider. They told us in the first part of this question that there was a total friction in the system of 44.1. And then when we read this one, they said that 14.7 of that is acting on the 10 kilogram block. So can I figure out how much friction is acting on the 20? How do I do that? Just subtract them. Whatever is left is the amount of friction that was acting on the 20 kilogram block. Okay, so that'll be my first calculation. Okay, is I'm just going to take the 44.1 and I'm going to subtract from that the 14.7. Okay, so the 29.4, that's how many newtons of friction there are on the 20 kilogram block. So I'm going to draw a free body diagram of the 20 kilogram block, okay, knowing that the force of friction on that is 29.4 newtons. Okay, the only other force pulling on the 20 kilogram block is the rope between the 10 and the 20, which is the one they want me to calculate the tension in. Everybody okay with that? All right. can I calculate the net force acting on the 20 kilogram block? Obviously, I can't do it using sum of all forces because I don't have all the forces. But is there another way to calculate net force? Using mass and acceleration, right? I already calculated the acceleration of all parts of this system is 0.36 meters per second squared. So that's the acceleration of this block. So I'm going to calculate the net force acting on the 20 kilogram block by going mass times acceleration. This will give me the net force acting on the block. All right, so I've got 7.2 newtons of net force. All right, now that I know that, can I find the force pulling the block forward? Okay. Have I done anything different than any of the other questions we've done? I did mass times acceleration, and then now I'm going to do vector sum of all forces. I did the same 2 steps that I've done in every other one, but what made this one more difficult was that I had to look deeper into the situation than I have in all the others. Okay, but in the end, it was still the same steps. Okay, but this is a more complex situation. That's where Newton gets difficult. I tried to tell you guys that the other day, but this illustrates it a little bit better. Okay, it's always the same idea, sum of all forces and m times a. But how do I get to those 2 steps? I have to be able to look into the situation and do it. Okay, so next step then is that F net equals the tension in the rope, okay, plus the force of friction, vector sum of all forces. All right, so I'm trying to find the tension, so I'm going to bring friction over. So I'm going to have F net minus the force of friction, which is negative because it's backwards, okay, equals tension. So that'll be our 29. Sorry, that was the friction, 29.4. Okay, our net force was 7.2, right? Yeah, 7.2. So I'm going to have 7.2 newtons minus negative 29.4. Okay. Whoop, missed the 9. All right, gives me 37 newtons. Okay, 2 significant figures here. So 37 newtons forward. Okay, everybody all right with that? Yes? Okay, now the other way to do this was to use the 10 kilogram block, right? And just so you know, we did get the same answer they got, right? Okay, so the other way to do this is using the 10 kilogram block. So if I draw a free body diagram of the 10 kilogram block, I have 55 newtons going forwards. They told me that originally. Okay, the rope attached to the first mast is pulling with 55 newtons. I have friction, 14.7 newtons, and what else? What's the other force pulling backwards on the 10 kilogram block? No, not the 20 kilogram friction, but just this rope. That rope pulls forwards on the 20 kilogram mass, but it pulls backwards on the 10. Okay, it's like towing a trailer. Okay? If you tow a trailer, it's harder work because you've got this other thing pulling backwards on you in addition to friction. You've got all that extra mass and inertia behind you. Okay, so there's also the tension in the rope, which is what the question wanted me to find. Okay, I found it using the 20 kilogram block. I'm going to find it using the 10 kilogram block. I'm going to get the same answer. Okay, so I'm going to first calculate what the net force on the 10 kilogram block is by going m times a. So 10 times 0.36, okay, is going to give me 3.6 newtons, okay, forward. So the net force on the 10 kilogram block is 3.6 newtons forward. Okay, F net is going to be the tension plus the force of friction plus 55 newtons, that forward force, okay, on the first block. So I'm looking for the tension, so I'm going to subtract these 2 numbers back over here. All right, so I'll have F net minus the force of friction minus 55 newtons equals T. So that's going to be 3.6 minus negative 14.7, because it's backwards, okay, minus positive 55. Okay, did I get 37 again? 37 newtons, right? Didn't matter which box I used, I got the same tension in the rope, which makes sense, I should. Okay, it's part of the same system. Okay, so that's where Newton's second law problems get difficult, is being able to see into a situation and understand what's going on, where are the forces, how are they pulling, okay, things like that, right, as opposed to the math. The math is always the same. Sum of all forces, mass times acceleration. Nothing's going to change on that. That's Newton's second law, okay? But how do we get to those? That can get pretty hairy. All right, try number 1. It's a little bit easier than that one, okay? Try it. So I'll blow it up a little bit so it's big enough to read. Okay, give it a try. Think. All right, so let's draw the situation, because that's what we're always supposed to do. Okay, I got 2 5-kilogram pails. They're connected and they're being lifted by some unknown force above them both. Now, the question tells me that the tension in this rope that connects the buckets is 60 newtons. All right, so that represents a 60 Newton force upwards on the bottom pail. Everybody okay with that? What force is pulling down on the bottom pail? Gravity. Can I calculate how big gravity on the bottom pail is? Yep. Right. So I can go 5 times 9.81, which should be 49. No, 5 times 9.81 will be 49.05? No. It's 49.05? No, it can't be. It's negative, yes. Yeah, negative. Okay, so there's my force of gravity downwards. I've got 60 newtons up and 49.05. But the question asks for the buckets plural. So is what I'm doing okay? Yes, because the buckets are part of a system, and all parts of the system have the same acceleration. If I can calculate the acceleration of any one part, that's the acceleration of the whole system. Okay, so that's what I've got to do here. I only have enough information to work with the bottom pail, so that's what I'm going to work with. And I'm going to say that since they're connected, they have to accelerate at the same rate. It would be impossible for the bottom pail to out-accelerate the top one. You ever seen a bottom pail catch a top pail? Like, it's just not going to happen, okay? Unless you like stop the top pail and then it goes past it, okay? Inertia maybe, but right, that's not what we're dealing with. We're dealing with the actual lifting portion, not a stopping portion, okay? During the lifting process, they accelerate at the same rate. If they don't, then one of the ropes breaks, okay? And then they're not a system anymore, right? So I'm going to calculate the net force using sum of all forces. So that's going to be 60 minus 49.05. Okay, and okay, so we got 5 times 9.81. Okay, and we're going to go 60 minus that. Okay, so we got 10.95 as our net force. 10.95 newtons upwards as our net force. Now, I want to find the acceleration of just this pail, so I'm going to divide that by the mass of just that pail to get the acceleration. Okay, so 10.95 divided by 5 kilograms of the pail. This thing is going to accelerate up at 2.2 meters per second squared. Okay, everybody all right with that? So again, same steps we've done on every other question, but I had to really look into the situation to figure out what I had to do. All right, visualization is the thing we have to work on. That's why we spend so much time on this. Okay, we still got some time yet, so don't pack up. Is this still a system? Yep, those two boxes are connected by a rope. They will accelerate at the same rate. Will they necessarily accelerate in the same direction? No. One's going to go up, one's going to go down. Okay, but we can calculate that, right? What's the only force acting in this system? Gravity. Does it affect the two boxes equally? It does not. Okay, because one box will have a greater weight than the other. All right, we'll talk about that one on Monday.